Let's get started. Okay, so a little bit laggy, but should be okay. And welcome to session 7. So again, for people who know, just bear with me for a sec. This is where we have everything, and Brian has already also posted a link to Hackaday project. Before I get started with today's topic, again, congrats to the people who submitted the katas to get the first certificate. And I got a couple really nice results tweeted. And just for people who missed it last time, we're doing a certificate give out, which is this vector graphic where you can use to print on anything you want, and is kind of a hacked Schrodinger's cat. And all you need to do is to find a quantum katas and then do a screenshot that you finished a whole set of katas, then post it on either Twitter or LinkedIn. You will get this. Of course, you need to tag these accounts and hashtags so that I will know. So today's topic is on algorithms. We start with the simplest, the earliest, one of the earliest algorithms, which is Deutsch's algorithm. So these are a set of algorithms that are really classically taught in academics, so in academia. They were developed in the past couple decades, and there were early algorithms that scientists were able to show the specific improvement compared to classical algorithm for specific tasks. So the Deutsch algorithm, what it's trying to solve is to figure out if a function is balanced or constant. Balanced just means that is not a 2-to-1 function, is 1-to-1. So one input gives out one output, and there's no repeated ambiguous result. When a function is constant, is a 2-to-1. So here is saying no matter what input you give, you will get the same value. So either your function output 1 or either it is 0. So don't worry that right now I'm just giving a short intro. If anything sounds confusing, we're gonna answer that later. And Deutsch-Jozsa is a expanded Deutsch algorithm for n qubits. And later on, you will also see some of the more complex algorithms that also tend to be more useful. So Groover's algorithm is a search algorithm for ordered list. And then also the Shor's algorithm you would use to factorize really large numbers. So there are not a lot of quantum algorithms that are distinctly different. These are some of the examples that are doing different things, and most of the later algorithms are developed based on those. Here is a link where you can find all kinds of other algorithms, and I hope that by your self-study of quantum computing, you will be able to come up with more useful algorithms in the future. And also, a lot of these are academic, and we need a lot more large-scale industry solutions. So keep that in mind while you learn these historic algorithms, but also the industry really needs more interesting and useful ones. Before we go to the algorithms, there's a concept called oracles. I very perplexed. Why do we call these things oracles? Like, I was trying to look up the definition of oracles. So there's the theological definition. So that's what this cartoon is trying to show. But also in quantum computing, we have this quantum oracles that's basically a black box. And there are also a lot of different ways to define it. Sometimes people say it's an operation that is used as input to another algorithm. Sometimes people say it's a represent classical functions that return real numbers instead of only a single bit. There's also definitions saying quantum operations which implement certain classical functions. These are just words and it's not that useful. So let's turn them into more intuitive pictures. A classical algorithm looks like this, where it takes some inputs and then you apply a function to the input and you get an output y. A quantum algorithm cannot use this kind of setup because this has no guarantee that this function f of x is reversible. And we introduced reversibility when we were talking about gates. When you're applying an operation onto your qubits, you need to make sure that they can reverse back. So this algorithm setup wouldn't be useful for quantum. So instead, in quantum algorithms, we build a setup like this, where your inputs are encoded into these qubits. And also, this output qubit y also goes through this black box. You will get your input qubits out through the box, and also your y qubit would become this y with a control knot with f of x. What does that also show? This is trying to give you a proof that you cannot set up a quantum algorithm like this. For example, in this case, if y is your f of x and you can have all these inputs of x, but it has a period. It goes from 0, 1, 2, 3, and then repeats. So in this case, you can get a f of x, but then you cannot reverse back. If you say you have a value of 3, you don't know if your x started with a 3 or a 7. So here is just trying to show you that instead, if you write your oracle black box in this way, then you can get a reverse. I wouldn't spend too much time showing you the derivation, but I'm keeping these slides here for you to look at later. So this is just trying to show you that if you set up your circuit like this, it would work, and it would be able to reverse back. If you do 2 of them in series, you get your initial inputs back to before. So don't worry about this too much. This is just showing you that in quantum algorithms, a lot of them, so I've shown you like teleportation algorithm before, we didn't need oracle, but a lot of those later algorithms that they need oracles, and this f of x is this classical function that we can get out of this black box, and it is also used to construct this black box. So let's just look at an actual example, this Deutsch-Jozsa algorithm then. And that's constructed by physicist David Deutsch and mathematician Richard Jozsa. At first sight, it seemed to be a very complex circuit. You have a bunch of input qubits, and you apply Hadamard gates onto all of them. And also, when you input those qubits, they all initialize to 0. So even including your input of the oracle, which is your classical output y, is encoded into this qubit. And it is also starting at 0, but then you do a flip, this x gate, that change it to 1, and do again a Hadamard gate. Then you throw all of these into this black box. When it comes out, you do a measurement of those input x qubits. And then you would know what your function f of x would be. So what Deutsch-Jozsa algorithm does is to find out if a function f of x is constant, which means f of x is either 0 or 1 for any given x. So constant 0 or constant 1. Or f of x could be balanced, which means half of the time f of x gives you an output of 0, and half of the time it gives you output 1. This is the setup for these algorithms. It does nothing else. It just tells us if a function is constant or balanced. It doesn't even tell you exactly what f of x is, but what this algorithm does is to tell you the nature of f of x. If you want to do this classically, you will have to test every single output given every single input. So you need to run your algorithm n times if you have n numbers. But in this case, even with n qubits, you just need to run your algorithm once and do the measurement for all these qubits. You will get the answer. So this is what it does much better than classically. A recap, what is H gate? In case you forgot, the H gate brings a 0 or 1 to this intermediate state that is a superposition of 0 and 1. What is a CNOT gate? It's, I haven't shown you a CNOT gate in Deutsch-Jozsa black box yet, but there is a CNOT, and what it does is to change the second qubit based on the first qubit. And what does H and the CNOT together do? Remember we discussed entanglement before. You would build a entanglement between these two qubits when you have a H and a CNOT. So intuitively, what Deutsch-Jozsa algorithm is doing, you are starting with some pure zero qubit state, and the H gate will change all of them into a superposition of 0 and 1s. And then this last qubit comes in. It started with 0, but then when you do an X gate on it, it would bring this negative sign into your system because H gate applied to a 1 state is the minus state. And then this black box is set up so that if f of x is constant, your oracle actually does nothing to your input qubits, these qubits here. So if that's the case, then when it goes out of the black box, nothing is changed. So applying a H gate to them will bring them back to where they started. So all of the outputs will be 0. However, if you want your black box to have this balanced function, then what it is doing is it actually entangles this qubit, this state, with any of the other state. So this then entanglement allows you to carry this negative sign over to your output of the oracle. And turns out that because this negative sign brought by this last qubit here, half of the time you would have a positive amplitude for all of the states being 0. But half of the time it will have a negative amplitude. So in fact, what this black box did, if the function is balanced, is that it creates this destructive interference for these states preserving. So the output, if you measure 0, 0, 0, 0, and if they are all 0, that tells you your function is constant. But if you measure any of those qubits being 1, if there's just even one state, you would know that your function is balanced. I know this is usually quite confusing when people first see it. Let's take another example, just because we have so many qubits here, the mathematics can get very lengthy. Let's reduce it down to the Deutsch algorithm, where we only have one input qubit. So this is what Deutsch algorithm does. It's trying to find, there are only two options now, only two qubits involved. If a function is balanced, it's either when x is 0, it gets f of x to 0, 1 to 1, or 0 becomes 1, 1 becomes 0. This is balanced. This is a 1-to-1 function. But if it is constant, say is always becoming 0, no matter your input, or it always becomes 1, both cases are telling you the function is constant. Yes? Mm-hmm.
You're frozen.
Is there a question?
Yeah, I said you are frozen, or you were frozen a second ago for the whole slide discussion.
Oh, we usually, yeah, I would present for half an hour and then we can have discussions and questions after. Is that okay?
Yeah, I was just saying your screen was frozen.
Oh, it is?
Yeah,
which?
it's fine now.
Oh, it's fine now? Okay. Thank you. Yeah. Yeah, it's a little laggy. I think next time I probably won't use this again. Let's see. So if you want to figure this out classically, you have to test each step. You need to do one run of your classical algorithm and then see what your end result is. If it is in this case, what happens next? You have to evaluate all of your possibilities. But as I mentioned earlier, if we turn it into a quantum algorithm, they would not need to be measured. They would not need to be run n times. So the Deutsch algorithm is just a 2-qubit version of Deutsch-Jozsa algorithm. So we would reduce this circuit into this below circuit, only 2 qubits involved. So that's much easier to follow and see what happens with the math. Okay, so the Deutsch algorithm is trying to find out if the function f of x is constant or balanced. And in fact, in here, you would replace it with a quantum algorithm that has an oracle in it. So you need to build an oracle based on the different possibilities of f of x. Let's see step by step. You can construct these 4 possibilities. So classically, you have constant 0, so f of x is 0, constant 1, f of x is 1. If it's balanced but same, is f of x will equal to x. But if it is balanced reverse, you will have a reverse of x. So these are the 4 probabilities. And you can write a truth table. This is how a constant with x would look like. But then now we're dealing with quantum algorithm. You need to even expand it to further. Your truth table would have all these possibilities written out. So if your x is 0, your y could be 0 or 1. And similarly with x is 1, you have 2 possible y values. And then you just write out, okay, constant is constant 0, then all of the x is 0. And then you calculate what y C naught or control, y is the control and f of x is target, you will know that if y is 0, f of x, this overall is 0. If y is 1, this result is 1. So you just do this calculation. So you see that this here is exactly the same as y. So then in this quantum oracle here, we do nothing. We just let the qubits pass through without making any gates. But if you had a constant one, you will notice that is the opposite to y. So all of these qubits got flipped for y. Then you know, okay, I'm gonna put a x gate to this second qubit to get this kind of truth table. But if it's balanced, which means half of the time it will have 0 and half of the time is 1. You see that you would be able to get this value if you had a C0 in between these qubits. So you can just try to construct this truth table, and you will see that this is what you need to do. With balanced reverse, is same there, but then you need to flip the qubit. So you put an x there. The significance here is that you see that if the function is, if they were constant, either constant 0 or 1, there's no interaction between the two qubits inside the oracle. But if your function is balanced, you have this C0 in between them. You connected the two qubits inside the black box. You can for sure write all of the steps out in mathematics, and I will highly recommend you do that at home to realize it looks difficult, but turned out is very, very easy. So you should try going through the math and try to reproduce it on your own to realize how this is done mathematically. So one way to study quantum computing is that people say shut up and calculate. So you will understand mathematically how it works. And that is my language, and I like doing this, but it's not always the same for everyone. And intuitively, this is intimidating. So what we can do is just intuitively looking at those gates, as I mentioned for Deutsch-Jozsa earlier, is that all you are doing is to make your state into a superposition and then introduce a negative sign. Then based on your oracle setup, you will either get your output 0 or your 0 will be cancelled out. So you will get 1 as your output. And those two cases correspond to function being constant or balanced. And I can even write this out more for you here. I made a note here for myself to not forget, is try to write out the steps. So this x plus 1 is this here. When your first qubit got a H gate on it, and now you are combining your system with a minus state, which is from your y here. And then what happens through this black box? So first you need to expand this. You will get a positive 0, 0, and then a negative 0, 1, positive 1, 0, and negative 1, 1. Okay, I'm writing with my finger here, it's not very pretty. My computer stopped recognizing my pen. So then what happens after you go through, say, I pick a balanced state just to prove the point. And what that truth table earlier told me, if I used this balanced same truth table, then what it's doing is based on my x, I would change y accordingly. So this would then becomes 0, 0, nothing changes, minus 0, 1, nothing changes because the first qubit is 0. But then your second one will become 1, 1. So this amplitude becomes positive. And then the last one is 1, 0. Then what's happening is that you have these interferent negative amplitudes here, so it will bring destructive interference. So if you want your first qubit to be 0, and then your first qubit to be 1, actually it doesn't really matter. So because the first qubit, you want to put it into a state where it is a superposition so that you can do a h to it to figure out if it is 0 or 1. So you would actually want to look at your first qubit being 0 and 1 there. So this gives you a positive state. And this one will give you a negative state. And then similarly, looking at this qubit here, this will give you a negative state. And this will give you a minus positive state. So what's happening here is the amplitude for the positive states are destructively interfering. So as a result, they would cancel each other out. And all you're left with is this minus state. And then when you do a h to it, you would then obtain your state 1. So it turns out that there's no possibility of obtaining 0 when you measure your first state if your function is balanced. So this is an exercise you should try to do at home to try the other cases. The intuition I want people to establish here is to understand that when this negative sign gets introduced, if it interacts with your one of the other qubits, and because of the h here and the c naught here, you're essentially entangling the two qubits inside this oracle, then your output would cancel. You will have half of the time that the zero's amplitude would be positive and half of the time negative. So you canceled, you destructively interfered them. But then if you don't mix those two qubits, you don't make them interact, then the top qubit would just come out without being altered. So in both constant case, you will get your output being 0. This is what Deutsch and Deutsch-Jozsa algorithms do. That's all it's trying to figure out is the nature of the function. So it's not a super useful algorithm. We don't use it anywhere. However, it is a very cool demonstration to show you this powerful effect when you have both superposition, interference, and entanglement involved in your algorithm. So classically, you will have to run your system multiple times, but then quantum-wise, you just need to run your algorithm once. So there are a couple of exercises that's related to today's topic you should look up on the quantum katas. And katas also has two options. It has its own Deutsch-Jozsa algorithm, katas, but it also has a tutorial option where it shows you some of the details. So there's the Deutsch-Jozsa, you should try it out. There's also the tutorials, which has a more explained step-by-step, previous. So I would recommend people go back and try these, which will help you understand what we discussed today. And another place you can look up is in the documentation page on the Microsoft's documentation site. We have the samples inside the documentation, and you can download the code from GitHub and try those out. So there are three exercises you can choose and pick to run. And then if you just look at the tutorial, how to set up the Deutsch-Jozsa algorithm, it's actually very straightforward. All it's asking you to do is to use code to set up this circuit. And the usefulness of the code is that as you grow your number of qubits, you wouldn't want to draw all of your qubits out, but you can just use the Q-sharp language, use code to directly write out. You have n qubits, and you can apply H and X gates, and you can apply oracle. This is exactly step by step trying to set up this qubit here. So you should go back and try to run this katas. That's it. To finish off, I'm announcing another certificate this Wednesday. The questions are as follows. This is less technical quiz. It's more of like a historic, fun entertainment. So here, I wonder who came up with the term quantum oracle, because it really kind of created this barrier for me to learn what this term is about. That's not in my culture. That's not in my vocabulary before. So if you're curious like me, please search around and see who came up with the term. And then I have embedded some characters in the comics. So on page 6, who is this person? And on page 26, who is this? So you can pick any of this and then tag me on social media as I mentioned earlier, and you will get another certificate, which I would announce on Wednesday. Okay, so that's it. Time for questions. Okay, a lot of messages here. Okay, I think is an issue with, okay, a lot of comments about OBS, yeah. Yeah, I think it's actually not a very good idea to use it. I may just switch back to Teams. And Isho mentioned, okay, Teams crashed. I don't know what you're talking about, Roberto. Where was I joking? Wonder what that was. Benjamin says he needs to brush up some math. Does proof of Deutsch's algorithm count as a homework for some? Sure, if you want to do that, yes. I would love to see you do that, Yisho. Yeah, thanks for the link for the katas. It's very easy to find. You can just search online quantum katas. It should just pop up as the first result. Yes, it is not hard. I basically give you a proof, an example of the proof for one of them, and you can pick any of the other options, like pick a constant one as your function, or pick reverse balanced as your function, and then try to do that. So what that list of activity there is to try to show you what comes out of the algorithm, and then see the probability of getting 0 as your output there. So this one is showing you when you have a constant 0 as your function, the result looks like this. And for sure you will measure a 0. And the amplitude there doesn't matter, because when you get probability, you square it. So it becomes positive. So probability of measuring 0 in this case is 1. So you should try that for other functions. And try Deutsch-Jozsa. Try to put multiple qubits in your circuit and see. Aha! Somebody's already answered that. That was Richard Feynman. So yeah, it's already answered. So that's not a challenge. Let's use the other two as your Wednesday claim for certificate. About Deutsch-Jozsa algorithm is just a theoretical algorithm, or it has been implemented in. You can implement it. You can exactly write out those circuits, but it's not being used anywhere. That's the thing. Because there's not like a practical case where you need to find out if your function is constant or balanced. So it's a very nice theoretical construct, and it was also one of the first algorithms that the quantum algorithms that was constructed and proved that for this particular case, it would perform better than classical algorithm. So it's just historic and famous, and everybody learns it in school. So once you understand, it does give you a lot of insight about entanglement and interference. Can I post the Twitch chat afterwards? No, well, I stopped streaming. We didn't use Twitch, so I don't think it's, yeah, I do still want to keep the Teams. I think it's really nice, and people are used to coming to here. Either I completely switch to Twitch, or I just use Teams by itself, because we just saw that earlier is really getting things stuck. So maybe my computer is not heavy duty enough. Great, thanks Benjamin. I'm glad you learned. And I'm also very glad to see when people posted the katas results, they really used a lot of documentations that we have available, and people learn from various sources. So that's definitely a good exercise for your self-learning. What is LOL? There are different interpretations. Aaron asks, what does constant or balance attribute help show that a function is related to Hilbert spaces, or that the function is reversible? The different concepts, and I don't know, maybe I don't know enough. I don't know the relation with Hilbert spaces here. For a function being reversible, I would recommend you go to those slides that describes oracles and how to make a quantum algorithm operation reversible. So you can't construct a quantum algorithm just in this linear classical sense. When it is quantum, you have to do this multiple qubits, and it is still linear, but this guarantees you that this oracle, this operation here is reversible. So just follow these 3 slides in your spare time, you will see. Okay, we can stick with Teams. Sorry, you show a crush on you. Yeah, it gets really laggy with OBS on. I'm asking my colleagues this week. I see, so the Deutsch-Jozsa algorithm is intended for classical inputs. Yeah, I think you can understand it this way. Yes, the qubits are encoding your classical info. Yeah, you can see here there are 3 bits encoded. So it's represented by 3 qubits here. That's right, for oracles. And it's not just for Deutsch-Jozsa. A lot of cases, that function f of x there is classical function. And you encoding the classical function and as well as bits into your qubits. In the classical computing, reversible computing also has a theoretical energy savings. I think I know what you mean. Yes, to have your gates being unitary, it makes it reversible, but also if you describe it as Hamiltonian, then it is related to energy. I think the problem is the video. Okay, still intertwined discussion about OBS and Deutsch-Jozsa. This is funny. So I would say Deutsch-Jozsa is both useful and useless. Useless in the sense that we are not using it in any practical problems, but useful to help us really have some insights into these quantum algorithms and see how entanglement and interference really play a role here. All right, that's it for today. Thank you, everybody.